Hey, in this last session we are going to calculate optimal sample size using the confidence interval method. And basically what we do is we use that formula that you've seen on the previous slides in the previous sessions, which was that formula to calculate sample error. And we use that to work backwards, to basically flip some components around, but it remains the same formula, flip it around so we can actually have sample size as the outcome of the equation. So to really understand what your sample size should be, there's a couple variables at play, a couple factors you need to know. Variability is in the picture again, so that's P times Q, as you know from previous sessions. That's the amount of agreement, disagreement you think there is between people in your sample. So how much variability do you expect there to be in your population? That's one thing to take into account. Acceptable sample error, E, is something you should determine beforehand as well, because of course lower sample error means more accuracy, and ideally you want very high accuracy of your results, but this comes at a cost. So in some cases, of course, you have to make a trade-off. You cannot have very high accuracy. So what is the most acceptable sample error for you? In other words, how much error are you willing to tolerate? And if you look right here, you could say maybe somewhere around here, maybe like a 3% sample error would be tolerable. That means you have to work with a sample size of 1,000 people. Next thing you have to take into account is the level of confidence you want in your results. If you want 95% confidence in your results, this comes with a z-score or a constant of 1.96. If you want higher confidence, if you want more confidence in your results, let's say 99%, that means your z-score, your constant, will be 2.58. Now, as you know from MIS, these numbers, actually you can find them in tables. I'm sure you worked with those tables in MIS before, but for this class it's fine if you just remember or retain these two numbers and what they correspond to. So basically what each of these z-scores corresponds with in terms of level of confidence. So these are the three main ingredients we need to determine proper sample size, and these are exactly also the main ingredients in that formula we used for sample error. That's what I mean with working backwards, so flipping that formula around. Here's the flipped formula. So you can see, like I said, the ingredients remain the same, but we flip them around. So now sample size is our outcome. We have P times Q, which is an indication of variability or variance in your sample right here. We have our constant Z, which we square, and then we have our sample error as well. So basically a measure for our accuracy squared as well in the denominator of the fraction. So you basically already know all the components of this equation. I'm not going to ask you to calculate anything, but for the sake of the example, I want to show you what a difference it makes if you have a different Z. So if you basically adopt a different level of confidence in your results, how that influences the overall sample size you need. So let's go back to our example of legalizing marijuana. Let's say, for example, you adopt a 95% confidence interval. As you know, because you memorized it, 95% confidence corresponds to a Z of 1.96. Okay, so we drop 1.96 in the formula right here. Now the other ingredient we need is variability, P times Q. And let's say for the sake of the example, we expect the worst possible variability. The worst possible variability, or the highest possible variability, is 50-50, right? You can never have a population or a sample that is more divided than 50% saying yes to something and 50% saying no. So the highest possible variability is 50-50. Then sample error, let's say this is of course a decision you make, a decision call. Let's say we adopt a 3% sample error. So with that formula, we can get to work, we can calculate all of this, and we get a sample size of 1,067 people required for your research here. Now I will show you that exact same formula with the exact same variability and the exact same sample size, but with a different confidence interval, and I'll show you how that results in a different sample size needed. So like I said, if we change the confidence interval from 95 to 99%, now we have to use the z-score 2.58 right here. Variability remains the same, 50-50, so we expect worst case scenario, and then our sample error, which we tolerate, is 3%. So we get to work, we calculate this formula, and now our sample size needed is 1,850 people. So of course this has implications. So that means you have to collect more data, more people, more respondents to your survey, let's say, just because you want a higher confidence in your results. Now, this is the essence of calculating sample size in a scientific way. Now, of course, there's a lot of rules of thumbs and a lot of frequently asked questions when it comes to actually calculating sample size. So some more pragmatic approaches to sample size. First of all, how do you even estimate the variability in a population? How do you even know? So one thing you could do is, like I did in the example on the previous slide, is expect the worst case scenario, which is 50-50. Variability can never be higher, at least if you work with percentages, than 50-50. It's a very high split, of course. That means literally your population or your sample is completely divided. There's not even a majority vote. There's a complete 50-50 split. Another thing you could do if you don't want to expect the worst case scenario is estimate it based on an educated guess. And this educated guess could come from previous studies. Maybe you've seen previous studies where they also did a referendum on legalizing marijuana or whatever topic you're working on, and you see what in that secondary data the variability appeared to be. So just adopt that same idea of variability. Another thing you could do is conduct a pilot study or some exploratory research. So maybe do a focus group with a variety of people where you can learn to understand what the dynamics really are, what the variability could be. So basically how many people would be in favor versus against a certain proposition. So this pilot study or this exploratory research could give you the input needed to make an educated guess in terms of variability. Another question I often get is, how do you even determine the amount of acceptable sample error? And this is tricky because, of course, researchers want to have as much precision as possible, whereas management wants to save some money on how much they spend on outsourcing that research. So how much error is a manager really willing to tolerate? How much do you want to compromise for your accuracy of your results? So of course, ideally you want as high accuracy as possible, especially in the medical field, but also of course in marketing. I mean, you want to be able to rely on your results. You want your results to be a truthful reflection of the actual imaginary population's results. So in that case, I would say find that compromise. 3% sample error or standard error of the sample is actually reasonable. So that's a trade-off you make. How do you decide on the level of confidence you use? 95 or 99? So these are conventions. Technically, you could even say 96% confidence or 97, right? But researchers typically use 95% and 99%. 95 is the most commonly adopted level of confidence. 99 is an extra strict measure of confidence, or basically you set the bar higher as a researcher because you want more confidence in your results, which again is important in life or death situations, but in marketing, usually we stick to 95% confidence. So on exams as well, when I don't specify it explicitly, then that means I assume a 95% confidence. So unless I explicitly say that we adopt 99% confidence, you can basically assume that 95% confidence is the standard. And now at the end, determining your sample size really comes down to a balance in relation to the cost of the data. So data collection costs money, so you want to, keep that in mind. If you want to give a $20 incentive per person, then with a sample size of 1,000 people, you already need a $20,000 budget. Now, of course, all these scientific methods of determining sample size are ideal, but they may not always be practical. So that's why there's a couple more easy rule of thumbs when it comes to sample size determination. What some people do is just a percentage. Let's say if a population is approximately 3 million people, then let's say our sample should be 5% of that, or 2% of that, or 1% of that, or 0.5% of that, just basically doing a percent rule of thumb sample size determination. This is of course arbitrary, but is commonly used in practice. Another thing you could do is follow conventions and beliefs, so adopt maybe at sample sizes that were used in the past. If a research company, for example, always sticks to 1,000 or 1,200 units in their sample, maybe it's a convention that they want to keep and they stick to that same sample size over time. Lastly, another determination factor could be just the cost. Some researchers or research institutions would go for as much as they can afford. So an all-you-can-afford type of decision-making process where you gather a sample as large as you can actually make it work budget-wise. So this was the class about sample size determination, the last session of this class about sampling. I hope everything was clear. If not, definitely let me know if you have any questions or listen to the recordings again. Kudos to you for lasting through this whole episode, because I know it's a little drier. It's definitely more difficult material, but it'll help you when you start working on your project and determining sample size. So